A good morning to you once again. I want to dwell into photorespiration again, just to emphasize certain aspects that I think I didn't emphasize enough yesterday. In the previous clip, which I sent yesterday, I concentrated more on describing the process. I concentrated more on explaining to you steps that unfold from the minute oxygen is attached to RBP to the minute carbon dioxide, or to the point carbon dioxide is finally released within the mitochondrion. Now, I'm just going to go slides by slides highlighting the most important things about photorespiration. By now, you should know that when we talk about photorespiration, we are talking a situation whereby oxygen instead of carbon dioxide is the one that is joined to RBP by the enzyme RBP carboxylase. That is when oxygen photorespiration takes place. Remember, the enzyme cannot discriminate between oxygen and carbon dioxide. So whatever comes first, or whatever is in higher concentration, is going to be the one that is joined to RUBP. So between oxygen and carbon dioxide, whichever is available in high concentration will be the one that is joined to RBP. The other thing that you must understand is whenever photorespiration is taking place, it reduces or it prevents the formation of glucose. And basically, when that happens, when the synthesis, the fixation of carbon dioxide, which result into the synthesis of glucose, is prevented by the process of photorespiration. This is a very, very unwanted situation for the plant, because less glucose are made, and therefore that means less productivity for the plant. It means less growth for the plant, and so on and so on. And basically, it also means bad news for us who depends on plants for so many things, food, and so on and so on. So the bottom aspect, I'm not going to deal with. I've already dealt with in the previous aspect. Suffice to say, when oxygen is the one that is joined to RBP by the same Rubisco enzyme, photorespiration starts occurring. And don't forget, whenever photorespiration is occurring, photosynthesis is not. And therefore, the synthesis of glucose is not taking place. I'm going to the next slide. That slide I'm going to skip because I dealt with yesterday. Now, on this slide, you will see it's written Rubisco has a high affinity for CO2 compared to oxygen. What that actually means is the enzyme actually attaches oxygen faster, attaches to carbon dioxide faster than oxygen. The problem, however, is that in the atmosphere, there is too much oxygen compared to carbon dioxide. The situation is somehow changing currently because of so much carbon dioxide being pumped into the atmosphere through industrial processes and this and that. But ordinarily, there is a lot of oxygen in the atmosphere compared to carbon dioxide. Therefore, the air that enters the leaf tends to have more oxygen than carbon dioxide. And therefore, it goes with logically, logically, if the air that enters the leaf has got more oxygen than carbon dioxide, it is going to be oxygen that is favored in terms of being joined to RBP as compared to carbon dioxide. That is what causes the problem of photorespiration. So that is a problem. In a situation where you have got more oxygen getting fixed instead of carbon dioxide, then you have got a photorespiration being exacerbated or increased or favored as compared to photosynthesis. The other thing that is very much important is that under high temperature conditions, normally temperatures must increase in order for photosynthesis to increase. Most enzymes work properly well when temperatures are a bit high. But unfortunately, in this particular instance, high temperature conditions makes oxygen to be more soluble. To be more soluble, remember what enters into the leaf is some kind of moisture. It's air combined with moisture. Oxygen becomes more soluble, it dissolves faster. Therefore, under high temperature conditions, oxygen is even favored more than carbon dioxide in terms of its movement into the leaf, and therefore in terms of its chances of being attached to RBP as compared to carbon dioxide. So what that means is higher temperature conditions favors photorespiration instead of photosynthesis. So therefore you need to have a mechanism that can sort of counter this photorespiration process. So basically, in brief, photorespiration is a very serious problem for plants, particularly those plants that fix carbon dioxide directly through the Calvin cycle. That what we mean is immediately when the CO2 enters into the leaf, it has to go directly into the Calvin cycle. You will understand what I'm talking about when we start dealing with the C4 plants in the next slide. You will see there are plants that do not deliver carbon dioxide straight into the Calvin cycle, even when that carbon dioxide is inside the leaf of the plant. Those are called C4 plants, and others are called chem plants. Now, these plants are at an advantage because within them they have got mechanisms built in that helps them to lower the process of photorespiration. So when the process of photorespiration is lowered by these plants and photosynthesis is therefore increased, these plants can survive in hot temperatures or temperatures with areas with higher temperatures, whereas those plants that cannot minimize photorespiration, particularly the so-called C3 plants, suffer in terms of productivity and growth under high temperature conditions. So basically, this slide is just showing you can see this is a typical leaf of the plant, the stomata, and so on and so on. So basically, under higher temperature conditions or under water stress problems, what are the plants going to do? The plants will close the stomata to prevent too much water being lost into the atmosphere through transpiration. Remember, the pore that is used, the stomatal pore that is used to allow carbon dioxide to enter into the leaf is the same pore that water moisture moves from the plant into the atmosphere through that same stomatal pore. So basically, a plant must balance between intaking carbon dioxide and losing too much water. That is a balancing act that a plant must try and do each and every time its stomatas open. So that is basically the issue. So when the stomata is closed, um, then there is no carbon dioxide entering into the leaf. And the carbon dioxide that is inside the leaf is going to be used up, because plants take in carbon dioxide so that they can fix it to make glucose molecules. They absorb it so that they can fix it to make glucose molecules. And if they fix all of the CO2 that is inside the leaf, then it means there will be no CO2 left. There will be no more glucose being formed. And plants must open their stomata to get more. So basically, that is basically what happened. So there are two types of plants, as you can see on this slide. The so-called C4 plants and the so-called chem plants. We are going to talk more about these plants in the next slide. Thank you.